Should we start now?
Yes.
Should we ask them to be quiet? No, they'll probably do it on their own. Bonjour.
Hi.
Je suis Chet Haase.
And I'm Romain Guy.
And we're going to talk about Kotlin today. We're going to talk about what is going on inside of Kotlin. So there's a lot of really cool things about Kotlin, but it's not necessarily obvious from the outside when you're using the features how they work. So we thought we would explore some of those. So what exactly is going on down there? That is us.
All right, how many of you are Kotlin developers? That's everyone. No, there's one guy, he's not sure. He was like, I don't know. All right, so I won't sell you Kotlin. We all know that Kotlin is awesome. That's why we're using it. Less boilerplate, blah, 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 whatever. Modern language features, so that's the interesting part. Basically, in this talk, what we're going to do is look at some of the features of Kotlin itself and look at what the compiler generates. It can be often quite surprising and might make you think twice about using some of those features. And then there's something coroutines, but we don't understand those. So maybe you can teach us.
It is magical, and it's not necessarily obvious how it's doing all of these things. So we want to do two things today. One is explore a bunch of features and see how they actually work under the covers, and the other is show you tools that you can use on Android or in general to find out this information for yourselves. So this is the way that we found out this information, and the techniques that you could use if you wanted to figure out more about the features that you're using. We're just doing a sampling of some of the interesting features. There's a lot more there that we could look into or that you could look into. We're actually going to do it in this order instead, and then the numbers are wrong. All right, so we're going to look at three techniques.
So the first one is we're going to look at the Kotlin bytecode itself, so the actual output of the Kotlin compiler. We are also going to look at the Java decompilation. So we're going to see how to do that, but you can go from the bytecode back to Java code, and sometimes it's just easier to understand what's going on because Kotlin hides a lot of stuff, as we just mentioned. And finally, the last tool we're going to use, the memory profiler in Android Studio. Most of the time, you probably won't need to worry about it, but it's just good in general to know how to use that tool, whether or not you want to understand Kotlin, or just because you want to make sure that your application is not using too much memory. So we're going to start with a very simple example. I mean, most of you are going to be familiar with that, obviously, since you're Kotlin developers. But if you declare a variable with the constant 5 in Kotlin, it's a type int, and in Java, it's a primitive type int. And now if we specifically specify the type, and we say it's an int in Kotlin, unsurprisingly, it's an int in Kotlin, and still a lowercase int, a primitive type in Java. And if you use the a nullable type in Kotlin, things change a little bit. So nullable types are different types in Kotlin, and they translate to a capital A integer in Java.
So how do we figure that out? We read the bytecode.
Clear for everyone?
And moving on. So the way we actually read the bytecode, that was the bytecode, but you can see it in a little more consumable form. So you go up into the menu of Android Studio and you choose the thing that says, I want to see the bytecode. And then whatever line the cursor is on at the time, so right there we have var I0 equals 5, and you can see the highlighted code in the bytecode. Some of it is just metadata talking about what line we're on. The actual code we're interested in, we'll get to in a second. There's another way that we can do this. We can use the Java P command line tool, and that'll spit out nicely formatted bytecode that you can look at alternatively if you don't happen to be in Studio. The Studio one's nice because it's all sort of integrated together, but choose whichever one works for you. So for this line of code, we have I0 equals 25. We have some metadata there, and then we have the two operations that are actually going on to do what we want, which is it's going to push a byte value extended to be an int onto the stack, and then it's going to pull that back off and put it into the first local variable.
And the point here, so we're going to show you quite a bit of bytecode today, but if you've never read bytecode or if you think it looks impressive or complicated, it's actually not. Most of the time, just by looking at the name of the operations, you can figure out what they do. So don't be afraid. It's super easy.
And if it's not obvious, there's this thing that we call the internet. That's what I used. All right, so again, we have this thing where we, instead of using type inference, we say that we want this to be an int. Exactly the same thing happens. We push 78 onto the stack. We pull it back off. We put it into the second local variable. And then here we have this nullable type. So things are a little bit different there. Starts out the same. We push a byte value of 14 onto the stack. But then we call this method value of, which looks like this. Value of returns an integer value. and it's going to box it. It takes the input value of the primitive int that was passed in, and then it boxes it into an integer and returns that. And then the store into the local variable doesn't go into an integer variable, it goes into a reference variable. So we're storing a reference because it's this box type instead of the primitive type.
But so I just said that reading bytecode is pretty easy, but what if you don't want to do that? Because even if it's easy, it can be very, very tedious. Here's a little joke from Chet, always the same joke. So you can use the bytecode decompiler, the one I mentioned a little earlier. So for instance, here we have some Kotlin code. It's very similar to what we just saw. We just assign values to integers, and then we print them, and your bytecode looks like this. And there's this decompile button at the top of the window, and when you click on it, it's going to give you the equivalent Java code. And again, most of the time, you probably don't need to go all the way to back to the Java code, but it will show you some of the things that Kotlin does and hides from you. And you can see here the translation between a nullable int type to an integer as far as the VM or the runtime is concerned.
All right, and then the third technique that we use to figure out some of the stuff is the memory profiler. So we've been doing a lot of work on the profilers in Android Studio over the last few years, and one of the ones that we worked on was memory profiling. So traditionally, Android had a large suite of tools, but suite is sort of an exaggeration of what it was. It was basically a lot of individual tools and utilities all over the place. Some were in the ADT plugin in Eclipse. Some got integrated into Android Studio over time. Some were command line tools. Some were running in DDMS. They were just sort of all over the time. One of my favorite tools was Allocation Tracker. It was a beautiful tool, but it ran all on its own. So a lot of that functionality has now been integrated together into the Android Studio profilers directly. So the profiler does several things. You can see what's actually going on with your heap over time. You can see the size that it has. There's a timeline view, and you can see at any particular point in time how big the heap is. You can see when garbage collections happened, and then what actually happened to the heap size as a result of that. You can catch leaks if you want. This used to be a complete hassle. You had to take a heap dump, probably transcode that into a different format, use some other external tool or some Eclipse tool for doing that. Or there are, I've heard there's actually applications and libraries that help you catch leaks as well. But now we can actually do that, again, integrated with Android Studio, and you can track allocations. So instead of using the standalone allocation tracker tool, you can actually do this thing directly in the memory profiler itself. So here's some simple code that I wrote by myself. So we have a tight loop. We're going to run 10,001 times through this loop, and each time we're going to take a primitive int value and we're going to assign it to something that is a nullable value. So we know from the previous example that this is going to be an integer type at the lower level. So what is actually going on? Let's take a look at the profiler. Down in the lower left of the IDE, we have some buttons down there. One of them is the profiler tool. We click on that, and then we see this view, and we see one of the 4 different profilers that we can use there. We're interested in particular in the memory one, so if you click in that area, then it expands to occupy the entire view there. And we can see over time, that's the heap size, and then there's this interesting bump that occurs over there. And we'd like to see what happens, what caused our memory to actually go up in the heap, and then what can we do about it. So if we drag our cursor over that area, it shows you down at the bottom, just like Allocation Tracker did, all of the allocations that occurred during that time. And if we look closely, we can see that integers were allocated to the tune of 9,873, which is interesting but unexpected, right? We're running in a tight loop 10,001 times. Why is it 9,873? It's close to 10,001, but I wouldn't really round it off to that number. So how did we get there? So this is sort of interesting. When does 10,001 not actually equal 10,001? So here's the tight loop that we're running in, and there's the number of allocations that were caused because of it. So it turns out that the value of methods that it calls into actually looks in a cache first. So when the runtime starts up, it actually caches values from, let's see, -128 to +127, sticks them in a cache because it knows that it's going to be a very common operation for someone to want that value, and so it just caches those and uses those statically throughout the runtime whenever it needs one of those. So what's going on in our code is, yes, we needed to use numbers from 0 up to 10,000, but the first 128 of those were cached. Therefore, we only get 9,873 that are allocated on the fly in our loop. All right, so back to the profiler view. We click on the one that we're interested in, And when we click on that, then it brings up all of the allocations for those 9,873 of them. And when we click on any one in particular, it will show you the call stack for where that allocation occurred. And then if we look closely, we can see that, in fact, it occurred in that tight little loop in the very simple code that we saw.
All right, so we're going to look at more complicated examples. And we're going to start with enums, because it's our favorite topic.
Yay, enums.
All right, so here we have an enum class called blend mode. It doesn't really matter what kind of enum it is. And what's interesting is what happens when you switch over an enum. So in Kotlin, we use the when keyword, and your code will look like this. So this one is interesting because it's not specific to Kotlin. It's also what Java compilers do. So there's no difference here between the two languages. So we have a simple function. It takes an enum value as a parameter. We do a switch on it. We iterate. We switch over all the possible values of the enum, and then we just call random functions that don't really matter for our use case. So what happens when you compile this? If you look at the bytecode, it looks a lot more complicated than you might expect. So it looks like this. The first thing it does, and here it's an example where we can't use the decompile button that we showed you earlier, because if you click the decompile button, you're going to see a switch in Java. So it's going to hide all that stuff from you. So here the first thing it does is called getStatic. So blending KT is my class, it's my file, and then there's this inner class called when_mappings that contains another inner class called enum_switch_mapping $0. And if you look at the signature at the end, it's an array of integers. So the first thing our code does is it fetches an array of integers from somewhere, and then it calls the ordinal method on your enum. And ordinal gives you the index of the value inside the enum that you've declared. And then it uses that ordinal value as an index inside that array that we just fetched. And finally, using the value that comes from the array, it does the actual switch in the bytecode. And if we look at, for instance, in case number 1, we jump to line number 3. Line number 3 invokes one of our functions in the switch. So if we look at this enum, at these mappings, it looks like this. So it's a class that was generated by the compiler, and it does contain a static array that has the same size as the number of values that we have inside our enum. And that class contains a static initializer, and you can see it does something really bizarre where it takes the index of each value of the enum and it assigns a constant to that entry in the array. The reason it has to do this is to keep enums compatible. So if you change the order of your enums and you recompile the class that declares the enum, but you don't recompile the call sites, things will still work, and that's why it needs this indirection. But so that's for one switch in our code. So what if we create a second one? So here I have a second method that does exactly the same thing. We switch over our enum, it just does something different. So here instead of calling functions, we just generate strings. If we go back to our mappings, you can see that now we have two arrays. There's a second array that was created for the switch, and it contains exactly the same mapping. So effectively, every time you're going to write a switch over an enum in your code, it's going to generate one of those arrays, and it will be initialized when the class is loaded. So it's going to allocate a bit of memory, do a bit of work. Of course, it's extremely cheap, but it can be of interest if you're writing really, really high-performance code and you have a really tight loop. What's going to happen is that this indirection will cause CPU cache misses, which might impact your performance. Now, 99.9999% of the time in your application, you don't need to care about this, but it's interesting. And so one last example. Here I have yet another switch. The only difference is I changed the order of the cases inside the switch. And if you look at the mappings that are generated, it created a third array, and you can see that the order of the mappings matches the switch. So again, it doesn't really matter like what the orders are. Even if we always switch in the same order, it's going to create a new array every single time.
It's important to note, too, that the overhead of the array creation and all the ordinal assignment, like all of that was because of the when, not because of the enums. The enum itself, if you just declare an enum at the Java class file level, you're just getting the Java class file enum implementation. It's when you actually do the switch on it that it creates the extra overhead there. Let's talk about lazy properties. So very common pattern in software. I may not need this thing ever, and maybe it's expensive to create, so I'll get to it later. Pattern, everybody's done this. So let's say, this is a really stupid example, but let's say I wanted to delay the creation of this int object, right? So instead of declaring 573, I want to wait until later and see if anybody actually needs this thing before I get around to it. So I have a private variable that's nullable, and then I have the actual variable. And then in the getter for the variable, if the private variable is null at that time, then we'll go ahead and assign it, and then return that in the variable. Straightforward. This makes no sense. Don't ever do this for an integer. But you can imagine a more complex data structure where potentially it would make sense. In fact,
what you're going to see, those slides were, we created those slides because during a code review at work, someone wanted to lazily allocate a rectangle, and we'll see why the way they were doing it was a bad idea.
So rectangle makes a little more sense because at least you're avoiding creating 4 values inside of this thing. It's a little more complicated data structure than just an int. But let's see what's actually going on. So if we look at the Java codes, decompiled code, it's straightforward. You get the same thing at the Java level that you do by doing the manual approach. But what if we use this really cool feature in Kotlin called lazy? Right? So here we say, here's a Lambda. I want you to run this whenever anybody tries to get the value. And it's going to avoid running that Lambda until it actually needs the value. So here's what happens inside. First of all, it creates an array of k-property values. So k-property is used for reflection in Kotlin because it has capabilities on properties that aren't in properties in Java, right? So you can do reflection on methods and fields and all the normal stuff in Java the way you normally could. But if we have more capabilities in Kotlin, how do they do that using the constraints of the Java language? Well, they have this other data structure, this other class called k-property that they can use instead. So lazy properties are an instantiation of something called delegated properties, and the general implementation of delegation in Kotlin uses k-property because it needs this ability to say, okay, here's information about this property, here's the class name, here's the type, and then you've got setters and getters where it can return this information. So to begin with, when you say, okay, I'm going to have this lazy thing, and it's going to assign according to the Lambda, it creates this array of k-properties and creates an individual k-property inside of there. So you've already got 2 allocations off the bat for the array as well as the property inside of it. Then you've got this creation of this lazy object. This will return something called capital L lazy.
It traps the Lambda that you've declared.
Right. And then inside of the getter, it says, okay, when somebody actually asks for this value, I'm going to call this get value and then return the int value inside of there. This is the chance for it to then call through the k-property mechanism using basically reflection to go in and do all this stuff. Fair amount of overhead just to get an int value. There is an optimization that they implemented. So using an extension function, they implemented get value specifically for lazy so that it doesn't have to call through reflection. Instead, it does the right thing and just calls into this get value method, which is implemented here. So this is better than reflection, but you still got a couple of conditions to walk through as well as a synchronized block just to make sure that the right thing is going to happen. And then in addition to that, you've got all of this initialization code just to set up this whole wired mechanism, all to avoid allocating an int. So don't do that.
And so, yeah, so back to our actual example, someone wanted to avoid the allocation of a rectangle, so 4 floats. And then I showed them the code that's generated, and by trying to avoid the allocation of 4 floats, you allocate way, 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 way more, and you generate a ton of code and classes that have to be initialized. So bylazy is great. Use it. Make sure you use it when you want to create expensive objects, so either extremely heavy objects in memory or objects that need a lot of initialization and it will take a lot of time to run through their constructor, for instance. Don't use it for strings or recs or simple classes like this. Not worth it.
It's not called lazy just because you're too lazy to type a little bit more code. All right, so sometimes you might be using lazy initialization, not because someone may not need that value, but just because I didn't want to assign it yet. Lateinit, well, so what happens there? Is that using a similar mechanism? Actually, this is pretty optimal, right? So in Kotlin, let's say we're creating a rectangle object at the Java class file level. It looks kind of how you would expect. It creates it on the fly, and then the getter for that just returns the object. For a lateinit variable instead, this b is going to be lateinited, and then we're going to refer to it later and say, okay, now set the value to be the following. And this is what it looks like at the class file level. All right, so we declared it, but we didn't assign a value to it. Good, that's kind of what we were after. And then in the getter, we use we depend upon the default Java implementation of assigning null to objects that have no value yet, and we just check whether this private variable has a value yet, and if it doesn't, if it equals null, then we're going to throw an exception because nobody should be getting this before it was assigned a value. Otherwise, we just return the variable. So it does the right thing in a fairly optimal way, so lateinit is good.
All right, now we're going to talk about Unsigned. So Unsigned is an experimental feature of Kotlin 1.3. It's the ability to use unsigned numbers. So on the JVM or on Art or with the Java programming language, all the numbers are signed except short, and even byte is signed, and I could spend the rest of the talk ranting about why this is a horrible idea, but this is not the topic, so let's go back to unsigned. Anyway, so if you want to use unsigned numbers in Kotlin, you can just use the U suffix. And unsigned can be extremely helpful because sometimes in your APIs, as part of your APIs, let's say that you expect a width and a height, and a width and a height cannot be negative. It is nice to be able to catch this kind of programming mistakes at the type system level. So unsigned can be super useful. So here we declare just two variables, A and B, they're unsigned. And then we just sum them in a new variable called C. So let's look at how what the generic code looks like. It looks like this. We just push an integer constant 43 and we store 42 and we store it as an integer. So what's interesting is that the compiler or the JetBrains folks realize that there's no difference in the way the CPU is going to handle unsigned and signed numbers. So they just rely on just all the integer operations that you find typically in your bytecode. So here we create a second constant, and when we add them, we load the two variables. Then we call iadd, which in bytecode means add two integers. But then there's one last thing. We invoke a static method called uint.constructor-impl. So unsigned numbers in Kotlin are implemented with a new experimental feature called inline classes. And we're going to look at inline classes themselves in a little bit in this talk. But here, so because it's an inline class, we call this function called constructor-impl. And if you look at the signature here in the corner, it takes an integer and returns an integer. And what does this do? So it's an extremely complex function. Here it is. It loads the parameter that you give it, and then it returns it. I'm still not sure why they do it this way, but every time you create an inline class, or at least an unsigned number, it's going to do this. Obviously, things like R8, ProGuard, or the JIT, or the AOT compilation with Art will get rid of this, but it's there in the bytecode. And unsigned are super efficient. Like I mentioned, they use the integer operations. So the addition uses iadd, subtraction is isub, multiplication is imul. The only one that's a little different is the division. It's using a static function that's part of the Kotlin standard library, and they have to do this because division works differently when it's signed or unsigned. Now, there can be other interesting surprises. So here we have two values. We have a signed value, Z, and an unsigned value, A, and we want to print them both. So let's look at what the bytecode looks like. So the first one, the signed value. I sold you the punchline. But anyway, so the signed value just called print line because there's an overload for integers, so the Kotlin compiler can just call that version. But obviously, the overload for integers that's part of the standard library doesn't know about unsigned numbers because, like I said, with the Java programming language, all the numbers are signed by default. So what they do here, instead, they use the overload that takes an object and they implement the toString function on this class called uint. So they have to box the number. So every time you're going to print an unsigned value, it's going to be boxed and you're going to have an allocation. And those are not cached, unlike integers in Java.
All right, let's talk about ranges. In particular, let's talk about that for loop. This is the most confusing thing, I think, when people see Kotlin for the first time, because we all grew up on for loops in C and C++ and Java, and they've always looked the same for all time, until we got to Kotlin.
I'm not sure if they all grew up on C.
Okay, well, you should have. All right. So this is one of the many ways, none of which pattern matched the thing I was looking for when I first encountered it. But you can say, for I in the following range, 0 to 10 inclusive, do the following thing. Very similar, except it skips the last one, so I 0 to 10 exclusive. Or we can just say, repeat the lambda 10 times. Or we can say, here's a range, sort of flip it around. So all of these kind of look the same to me if you squint. So let's see what they actually look like in code. So at the class file level, that one does exactly what I was after. It says, yep, you've got some integer values, and I'm going to iterate through them. Same thing, except we don't go through the last value there. Repeat, very similar. It's going to go 10 times and do the following thing. And then the last one, a little bit different. So it is going to actually create a range object and then an iterator out of that. So doing a couple of allocations kind of looks the same. It's just the other way around, but it's actually going to end up creating objects on your behalf.
Right. There's an extra feature of ranges called step. So, in Java, let's say you want to go from 0 to 10, but you want to increment I by 2. You just say I plus equal 2. So in Kotlin, you have to write step 2 on the range. And we saw that the I in 0.10 generates a loop that's perfectly fine. It's what you would expect in the bytecode. But if you just add that step 2, here's what you get instead. So it creates an int range, just like with the iterator we just saw, and it casts it to an int progression, gets something else out of it, then it calls get first, get last, and get step on it. So that will return 0, 10, and 2, the constants you wrote in your code, but for some reason we have to do all of this at runtime again.
I think it's compiler people being very clever.
Or very thorough.
Yeah.
Then it makes sure that your range makes sense, that you're not starting before the end or stuff like that. And finally, it has a while-true loop where they just exit when you reach the end. So interestingly, with step 2, sure, let's say that they're going to do all that stuff. If you write step 1, so it's exactly the same as not writing step, you're also going to get all of this. So make sure you never use step 1. So I mentioned inline classes before. So what inline classes are, they're special types of classes. They're kind of like data classes, but they can contain only one field. And what the compiler will do, and it's kind of in the name, inline classes, the class itself will never appear in the bytecode, or almost never appear. So here I have a very simple example. I created a color class to wrap the color ints that we use a lot of Android. So it's very convenient because I was able to create my own properties that can extract the alpha, the red, the green, and the blue channels. So you don't have to do this kind of stuff yourself. You don't have to invoke static functions. And here's how you use an inline class. So in my main, I create an instance. I pass some constant. And then I call a print color function that I've created passing that class. And you can see the print color function at the top. It receives a color instance, and then I just print the different channels. Now let's look at the bytecode. So when we create the class, we first load a constant on the stack. So that's the LDC here. That's my color. It doesn't really matter what it is. Then we invoke a static function. It's color.constructor-impl. And you can see it takes an int and returns an int. So it's the same exact one that we saw for unsigned numbers. It's going to load the parameter and return it. So it's completely useless. And finally, it calls our print color function. But if you look at the name, now it's called print color dash some crappy hash code of some kind. And it doesn't take a color instance anymore. What it does, it takes an integer, an int. So it's really nice because, as the name suggests with inline classes, the class is gone. It's not there anymore. We're just working on an int, except in our code, we can treat it as a class and have code that's easier to read and to maintain. So far, so good. Now let's take a look at this particular example. So we have two inline class instances, A and B, and I just want to print whether or not they're equal. And there are two ways we could do that. We could use equal, which in Kotlin will basically call dot equals. And then we could also call dot equals directly. Now here's what happens when you do this. So in the first case, with the equal operator, the first thing it's going to do is call this method called box-impl. It takes an int and returns a color instance. So here we boxed our class. We just allocated a new instance. And then on line 3 and 4, it does the exact same thing for the other variables. So both A and B have been boxed. And finally, it calls a static function inside the Kotlin library called requal that takes two objects and does the equal comparison. And it does that because equal in Kotlin has some guarantee around nullability. Obviously, in the code I just wrote, there was no way that the variables could be null, but the compiler doesn't try to optimize this. So again, most of the time you won't even have to care about this, but if you're going to do a ton of comparisons between inline classes, let's say in a very tight loop because you're doing image processing, you're going to end up generating a lot of garbage and triggering garbage collection for no reason whatsoever. Now, if instead of using equal, you call a.equals b, you can see that one of the values does not get boxed, but the other one does. So we just dropped half of the allocations. And it's probably because here there's some guarantee about the nullability that the compiler can infer. So it calls a slightly different version of the equality function. So just be careful with equality and inline classes.
Simple example, different ways of declaring arrays with slightly different implications. So we have the int array of with some values in there, and at the Java class file level, it's going to give you a primitive array, which is probably what I was looking for there. If we don't actually tell it int array of, though, and we let it infer, I would think, type inference, those are obviously ints, so we're probably going to get the same thing. Not so much, right? It's going to box that and give us an integer array at the class file level. In the third case here, we're going to run a Lambda to create the values, and that actually does what I was looking for the first time around. It's going to do the int array instead.
So speaking of lambdas, here's an interesting example. It's more of a gotcha than some inefficiency in the bytecode. So here we have let's say a Java API, like on Android, we have a widget, and you can add and remove listeners. And our listener is just an interface with a single method on it, on event, that takes a widget instance. So what happens when we use this from Kotlin? So here we create an instance of our widget. Then we declare our listener as a lambda in Kotlin, and we take a widget as a parameter, and we just want to let type inference do its job. And Kotlin, when we call add listener, it will see that this matches the signature of the listener in the widget, and it will just work. Unfortunately, so when we call add listener and we print the number of listeners, we're going to see that we have one listener. But then when I call remove listener and I print the number of listeners, it's still going to say that we have one listener, and it's not a bug in my code. So to understand what's going on, we have to look again at the generated code by the compiler. So what happens is that lambda is not at the bytecode level an instance of the interface that we've declared in our widget. So what Kotlin will do is your lambda is a function one, so it's a lambda that takes one parameter, hence the one. And then it will wrap it into with that weird class called lambdas kt sam widget listener 0, and then finally pass that wrapper to add listener. And obviously it's going to do the same when you call remove listener. So because it created two different wrappers, you're adding one listener and you're trying to remove a different listener, and that's why the number of listeners doesn't change on the widget. The fix for this is to explicitly state the type of your lambda and not let the single abstract method type inference do its job.
Extension functions, subclasses. So I think people using Kotlin know how this works, but why? So let's have a simple class called superclass, and then we're going to have a subclass of that I called subclass. We're going to instantiate these. Sorry, we're going to declare extension methods for these, get identifier. So for the superclass, we're going to return something that says super. Subclass, we're going to return a string that says sub. And then we're going to instantiate. So we have one instance that is an instance of the superclass, another instance of the subclass, another instance of the subclass, but cast as a superclass. And then the question is, what happens when we call get identifier on each of these? And then there's a fourth example here where we just do a runtime cast instead of casting it at declaration time. So the first one, when we call get identifier on the superclass, it's going to return, okay, 3 people are awake. All right, super, yes. And subclass is going to return, hey, and subclass cast as super is going to return super. All right, and finally, runtime, same thing. So what's actually going on here? Extension methods are are implemented at the Java class file level as static methods, right, that take a particular type. So we have a static method for get identifier for the superclass that takes a superclass object. And we have another one for the subclass that takes a subclass object. So in our first example, when we call get identifier on the super, obviously it's going to call itself with a super object, call into the static method that takes one of those and return super. Same thing for the subclass, calling into the other static method. The other one, yes, it is a subclass. However, we have told the runtime that it is to be treated as a superclass, which means it gets passed into the static method that takes the superclass. And same time for the one that was cast at runtime.
Default parameters, it's an amazing feature of Kotlin. When you create an extremely useful function such as this one, it takes 2 floats and returns the 2 floats added together. But let's say I don't want to have to specify the 2 values every time, so I specify default values on my function. So how does this work internally? So here's what happens. First, it generates the method that you would expect, a method that takes the 2 floats and adds them, and there's no default parameters. And then it creates a second function called adder $default. It takes our 2 floats, and it takes another 2 parameters. There's an integer, and then there's an object. I'm still not quite sure what the object is for. It's probably to tag the function and make sure like it doesn't clash with any other declaration, because the Kotlin compiler, as far as I can tell, will always pass null for the object. But the integer is interesting. It's actually a bit field, and every bit that's set on that integer tells you which one of the parameters you haven't set at the call site. So for instance, here we say if that integer n1 is different from 0, that means we haven't set the first parameter of the function, so we're going to use the default value that we've created. And then finally, when we've assigned all the default values, if needed, we call the actual implementation of our function. So it's interesting because here it's going to do a lot of branching and jumping through hoops just to be able to handle the default values. And so, yeah, let's see different ways of calling that function. So if we call the function without specifying any value, we're going to see that it's going to pass 0 for the two parameters because we didn't specify them. And the bit field is set to 3, so it's the bit 1 and the bit 2 together that are set. If we specify the first parameter, we're going to see the value of our first parameter and the bit field becomes 2. Same thing for the second parameter. And then finally, if we specify both values, the compiler is going to completely skip all that extra work and call the function that does the actual real work. Of course, an integer, so they use a bit field, which is pretty smart, but there's only 32 bits. So what happens if you have 33 parameters, like this?
Don't do this.
Well, I mean, you could. You probably shouldn't. But just in case, let's see what happens. So what happens is actually very interesting. The compiler will generate 2 extra ints. So every time you add 32 parameters to your function, you're going to get another bit field added. Honestly, I was expecting this to just refuse to compile, saying like, hey, you have too many parameters, don't do this. But it works.
What's better than a bit field? 2 bit fields.
All right. Last example, coroutines. So let's start with a suspend function. We have a very simple suspend function here that prints that we're computing something and we're simulating heavy work by just calling delay. So we wait for 1 second. Then I have my main function. First, we print that we're launching the coroutines. Then I launch my coroutine and I call the suspend function twice. And then finally, we call exit. So unsurprisingly, this code will print launching coroutine. We call compute twice. We see that in the console. And finally, we exit. But how are coroutines implemented? It's actually very interesting. I'm not going to show you all the bytecode that's generated because there's quite a bit. But effectively, coroutines are implemented as a state machine. And if you look at the decompiled code, it looks like this. There's a class that implements an invoke suspend function. And the first thing that this class does is switch on a field, an internal field called label. And that's the state of the state machine. And you can see that when we take the first case, so that label starts at 0, and when we take the first case, we're going to set the label to 1, so we step to the next state in the state machine, and we call our first compute function in our coroutine. And you can see that compute suspend function can return a constant called suspended. And if we're suspended, because we call delay in our example, we're just going to return from the state machine. Here we go, and if we're in the state number 1, we're going to advance something and call compute a second time. And to see exactly what's going on, in this example, I went and hacked the bytecode, so this is the actual bytecode generated by the compiler, and I did all that stuff. You don't really need to care about what it's doing. Basically, I just added prints. So I added a print at the beginning of this invoke suspend function, at the beginning of the state machine, to see how often it's called and what is the state of the state machine every time it's called. So remember, this was what was printed in the console. We're launching the coroutine. We call the suspend function once. We call it a second time, and then we exit. And after hacking the bytecode, this is what we see. So we launch the coroutine. We enter the state machine, and the current state is set to 0. Then we invoke our compute function. And then remember, because I called delay, we return from the state function. And at some point later, when the scheduler of coroutines is ready, we re-enter our invoke suspend function with a different state. And we can see it here, we're on state number 1. We call our second suspend function, and then we enter the state machine one final time, a third time, before finally exiting.
All right, so all this information about all of this overhead that Kotlin creates in some special corner cases of some snazzy features. The question is, should you care? So over the last couple of years, we went out and gave talks about the garbage collector on Android and how the runtime has gotten much faster, and you really shouldn't worry about things like allocating and collecting because honestly, we're past that now and the runtime's great. So what about all this overhead? Did we lie to you? Did we tell you all this stuff that wasn't true and you actually need to care about? No. Actually, we're telling the truth. The runtime is really fast, especially allocation and collection.
See, that's weird. Your slide says, did you lie to us? And it's followed by true, so we lied to them? This is confusing. We may or may not have lied to you. We'll get back to you on that.
I think my state machine was wrong. So I find it really interesting to actually understand what is going on in the system. In particular, it's good to understand overhead. In particular, you need to know whether this is an overhead that you can consume at any given point in your code. If you're in an inner loop where performance really matters, then at some point you may really care about things like cache misses or things like allocation of temporary objects, which are contributing, however small, to the overall runtime performance characteristics of your application. So it's good to know what's going on in case it matters. It probably doesn't. But if you're going to go ahead and use lazy because you didn't want to allocate a rect, maybe knowing what's actually going on in the hood will help you make the right decision there instead. We have
5 minutes.
Well, they said we can go a couple minutes over. Let's try to take a question or two, and then we'll shut it down after that. So if there's a question. Yes? What about sealed classes?
I haven't looked at it, but I would be very surprised if sealed classes generate code that is unexpected. It's probably just it's a language feature. It's like when the compiler generates the code that it does the checking, but shouldn't create more bytecode. But we should check.
When we were looking into this, we looked at a plethora of different features in Kotlin, and it was kind of amazing the extent to which it actually does what you would want it to. Like, it really does make a lot of very good decisions about how to transcode Kotlin feature into pretty optimal bytecode. Those weren't the ones we wanted to talk about because it's interesting to look at the corner cases where it wasn't obvious, the overhead.
And there are tools that will help. For instance, something we didn't talk about is when you have a non-nullable type in Kotlin, every time you enter a function that takes a non-nullable type as a parameter, it will insert a static function call to check that the parameter is not null. And it can be a little inefficient because sometimes your code is invoked only from Kotlin and the compiler has already checked that you cannot pass a null at this point, but they had to do this for compatibility with the JVM or the Art runtime. And so the tool called Art, that is now, I think, turned on by default in Android Studio 3.4, will actually look at your entire program and remove all the null checks if it can prove that they are unnecessary. So, even all the things we've shown you, what actually happens on runtime can be different because of the JIT, because of ahead-of-time compilation, or because of R8 if you run R8 on your code. R8 already does a lot of optimizations that are very, very interesting when you use Kotlin.
Shall we take one more question?
Yes.
Before the person standing over there gets mad at us? Hi.
Did you feed these back to JetBrains, and is there something they could do to fix some of these? Or?
So we personally did not feed that back to JetBrains, but we have a few people at Google on Android who work on the Kotlin compiler. They make contributions. And we also have Jake Wharton, for instance, helps the R8 team. He spends a lot of time looking at these kind of bytecode patterns and identifies things we can optimize. And honestly, Kotlin has gotten better over time. And a lot of this, like we said, doesn't really matter. But some things like loops, I think in the very first versions of Kotlin, they were really, really bad. And they got better. So every new version of Kotlin brings improvements.
Thanks.
All right. Thank you very much.
Thank you.